response, accuracy, robustness, and stability. So I've gone through this. And many of this can only be achieved under high gain scenario. Okay, so remember that. And there are limitations as well. Okay, high gain scenario, which is you are limited by plant capacity and also your measurement noise. Okay, so if you have lousy measurement sensors, alright, high gain will just amplify them. Okay, so this is very basic. Your power purpose lecture. What is more important is you used to do plot diagrams, alright? With a single degree of freedom, but now we are looking at how to analyze. Okay? In addition to this single degree of freedom, the stability of the system. So previously, in single input, single output SISO scenarios, we use stability tools like Nyquist plots, Bode plots, and rollovers. Yeah? Okay, for this course, there's something on top of that, which is the sensitivity function S and the complementary sensitivity function T. Okay, so we'll go through the derivation of this. And in addition, we talk about a second degree of freedom control structure. Alright? So for those who have read part 2, the notes, that these are reading are supposed to print out and read, you will see that in the text it talks about 2 degrees of freedom. Okay? What's the 2 degrees of freedom? Because now, alright, in addition to the ability to actually design C for controller, we can also have another block here, F, which is a pre-printer that can use the shape of command response. Okay, so that's what we call 2 degrees of freedom. Alright, and on top of that, we have external disturbance and also measurement noise. Okay, and you recall that we went into a lot of detail about how do you actually derive the relationship between the output Y, the reference R, disturbance D, and measurement noise N. Okay, year on year, there's always been this question about derive the relationship. Okay, and define what are the signals. Okay, so I'm not going to derive these transfer functions all over again because we have done so much time. Okay, and with the transfer function, you'll be able to tell that the sensitivity function S, okay, determines the amplification of disturbance of the output. Yeah, so if S is small, amplification doesn't really go to the output. Yes? And the complementary sensitivity function T determines the effect of measurement noise and also how well the output tracks the command reference. Okay, so there's a dilemma here. You don't want the disturbance, you don't want the measurement noise, right? You don't like measurement noise. But you still like the output to track your command response. Yes? Okay? So if you look at a low pass plant, alright, we have gone through this into a lot of detail, so we don't go through it again. We will plot the sensitivity function and the complementary sensitivity function. This is what it will look like. Okay, for S and T. Alright? So for sensitivity function, you see that it starts from very low values and low frequencies, and it saturates to 1, high frequencies for low pass plant. Okay, we've gone through this last lecture. And in this range, so that S is small. Okay? See that I write there that disturbance D is not amplified. Okay, you can understand this because if S is less than 1, it's 0 point something, right? Okay, your disturbance D is not amplified. For complementary sensitivity function, you observe that for low frequencies, T is almost 1. That's good because it tells you that your output is tracking your command response very well. Yeah, because Y is R. F-R. Okay? But in this range, your measurement noise is also present. Okay? And the next thing you'll notice is that on the transfer function, S plus T is 1. Alright? Okay, Okay, you have also observed that because of this dilemma between tracking the response and also the need to vary of measurement noise, probably you need very good low noise measurement sensors at low frequency range. Okay, so you filter away the noise with the external device. Alright? Okay? Now what I'm going to do is try to recollect for you what happened in the last 30 minutes of the previous lecture, right? Okay, so recall when we said margins, yeah? And what does stability margins you look at? You must only look at gain and phase. Okay, but now what we are telling you is that in addition to gain and phase, you also need to check those frequency points that are very near to the stability point -1. Okay, and how do you check that? We use the vector, so-called modulus margin Sm. Alright, and we did discuss how Sm, the vector modulus margin, is related to the sensitivity function. Okay? And that was done in a lot of detail last lecture, so we will not do it again. But there are always bound to be people who will just look at me and say that I don't recall what you have said last lecture, right? Okay, so this is what we said. The vector margin, alright, which is the distance, okay, of the frequency point on the negative plot L. Okay, that is nearest to -1. Alright, so we can define the vector margin to be the distance. Okay, from of the frequency point that nearest to -1 like this, you can derive that this is equivalent to 1 over the maximum value of the sensitivity function. Alright, and with this inverse relationship, you are aware that okay, you don't want your Nyquist plot to be near -1. Okay, you don't want your Sm, the vector margin, to be small. Okay, so if you want that to be small, you do not want the sensitivity function to. Okay, and likewise for the inverse Nyquist plot 1 over L. Okay, we are saying the same thing. So we will define another margin, Rm, okay, which tells you the distance from the frequency point on 1 over L away from -1. Okay, so we will define this, the distance, the minimum distance from 1 over L to -1 is Rm. You can work out that there's also an inverse relationship between Rm and the complementary sensitivity function. Okay, and likewise, you want your Nyquist plot to be far away from -1. You want the inverse Nyquist plot to be far away from -1 as well. Right? Because if L is near -1, 1 over L is near -1. Okay? So you want to avoid this case. Okay, you want to avoid a low Rm, hence you also avoid picking in T. Alright? Here I can show you a simulation. Okay, it's a bit small. I can see right there on the screen. But what do I have? This is a closed loop is a closed system. My plant is just unity gain of 1. Okay, there's nothing, it's just a purely of 1. My controller, I only accept that as my minus 1. I pass a sine wave E. So if I pass a sine wave E, what do I expect to see at output? Another sine wave, right? Depending on the gain, the amplitude would change. Okay? Alright, so if I have my controller at minus 1. Okay, this is what you see, which is marginal stability, right? Okay, so if you have a controller gain at 1, okay, this is stable. Or 0.5. Okay, still stable. But when you get nearer to minus 1, okay, start to say it's marginal. And if you go above minus 1, so you basically move your root locus to beyond the minus 1 point. So you go minus 1.05. And it goes crazy. This is just shooting up exponentially. Alright? So this is just to tell you, okay, why we want to stay far away from the minus 1 point. Okay? Alright, if you can understand this, the next thing we did was to talk about okay, so now let's say, alright, I have my microscope. Original microscope. Alright, I'm just trying to explain to you in further detail, so you don't have to copy this, just listen. Alright, this is all in your journal. Okay? Now what's L naught? L naught is just a controller gain, right? Because L naught is open loop transfer function times P naught, original plant. Okay? L naught is open loop transfer function, so it's the controller gain times P naught, which is the original plant. So right now, imagine that I'm telling you that this plant, this robotic arm, after some rotations has degraded through wear and tear. So instead of P naught, let's change to another set of dynamics. So it's now E. So L naught, let's change to L, which is C, E, J. Okay? And imagine if this was the minus 1 point. Alright? Now my L could possibly be like this. Okay? And I want to understand now. When I first designed my C for L naught in my control system, now that my P naught has changed to C, okay, is my system still stable? Okay, this is what I want to understand. Alright? So how do you do that? Okay? And remember we talked about the Doyle's stability criterion. Okay, right now what we're trying to say is for L naught initially, okay, let's say that the nearest frequency reference point to -1 was here. Okay, so this was the original SM. Yeah? And now, because the path has changed, let's just say that now SM2 is. Okay? Alright, I want to understand if the system is too stable. So we say that if the difference between the new path, the new open loop transfer function, from the original open loop transfer function, is less than SM. They are actually SM1 original piece. Okay, it is less than SM. For all frequencies, okay, the system is stable in a sufficient way. Alright? Okay, so this is the criterion. Alright, and is it sufficient just to say that you want to ensure the Nyquist plot, the new Nyquist plot, the new open loop transfer function satisfies this criteria? It's probably not sufficient, right? Because remember we're saying that you want to keep L away from -1. You want to keep 1 over L away from -1 as well. Yes? Alright? So you would like to do the same thing for 1 over L. Okay, so we say that for 1 over L, alright, minus the original universe, okay, should be less than Rm. Alright? Okay, and from these two equations, okay, you'll be able to fit SM1, so this 1, this 2. Alright, these are the two equations that you see out here. Alright? And these are all sufficient conditions for stability. Okay, why sufficient? Because we're saying that it's not so tight, it's just inequality sign. So from 1, okay, you can derive that this should be less than 1 plus okay, so equation 2, 1 over L is less than 1 plus 1 over L. Okay, and next what you need to do is you can also further relate these two margins to your sensitivity functions. Yeah, because you can understand that the margins they have an inverse relationship with sensitivity functions. Okay, so from 3 and 4. Alright, just divide rho by L naught and 1 over L naught. Alright. Okay, you can work out that this is less than 1 over T. Okay, and for this case, 1 over L.
She asked whether she understood.
As not J
I
omega.
think his head or in F40.
Okay? Alright? If you can do this, this is noise stability criteria, the sufficient condition. Okay? And in the exam, you will be asked to derive a necessary and sufficient condition for stability. Okay, under perturbation of the plant. What do you do next? You just define that if 1 over T and 1 over S are bounded in regions W1 and W2, so you change the inequality sign to less than or equals to, it becomes a necessary and stability, sufficient condition for stability. Alright?
I see it. Okay? So this is not rocket science, it's just simple math. Alright? Okay, so I was just saying, how do you change this from sufficient to necessary and sufficient? Okay, replace this part here by less than or equals to W1 J omega, which is a bounded region. Replace this part here by less than or equals to W2 J omega, which is another bounded region for S. Okay? And then it becomes necessary and sufficient for stability. Okay, so if 1 over S was bounded by W2, okay, so meaning everything, every single point for 1 over S J omega has to be inside this region, this circle called W2. Alright? Can you imagine that if this region W2 is exactly equals to 1 over S now. Alright? The smallest possible perturbation that you may have will just destabilize the system. Okay? We said that the necessary and sufficient condition for stability is 1 over S has to be totally kept within the region called W2. Alright, so if the region is right on the boundary of S, just any minute or smallest ever possible perturbation that you add to the system can destabilize it. Alright, so this is what I'm trying to say in this particular slide. We're going to draw a plot of S in dB scale over frequency. Okay, you can also see that for low values of S below 1, okay, we can allow large perturbations because S is small. Okay? For S restricted close to 1, we cannot allow perturbations. We cannot allow external disturbances to the system because any of that will just destabilize the system. Okay? Alright? Any questions? I but this is very difficult for you to get. It's very difficult for you to comprehend. But in layman terms, what I'm trying to tell you is mathematically, when we prove for necessary and stability conditions, when you are not sure if you have a group of frequency points, okay, you don't know where they are, what's the range, but you can define a group of frequency points. Alright? And you want to make sure that it satisfies a certain condition. What you do is you actually define another region that will encapsulate all of these points inside. Okay? So if you happen to have that region, the boundary that is right at one of your frequency point, which is this case, so it's exactly at the boundary. Alright, just a small perturbation to your system will actually push you out of the boundary. So you no longer satisfy the stability condition. Okay, just understand that. Alright, so if that's the case, then with the plot of sensitivity function, you can also understand that there are two regions here, whereby you can allow large perturbations, and the other region whereby you cannot allow any perturbation at all. Alright? So with this, we have a robustness test that can be defined. So we define delta L and the inverse of delta L as the left-hand side of your stability criterion. Okay, for the lattice plot and the first lattice plot. Alright, and we say that the perturbed closed loop system is stable. Alright, for all frequency omega being a real number. Okay, if you have this or this. Alright, this is still the Doi stability criterion. It's just that we are rewriting the left hand side, okay, as delta L inverse. Okay, no difference. This is just this. There's no change. You're going to draw it in a plot.
I don't believe.
Okay? Alright? Basically from Doyle's criterion, we know that delta L inverse has to be less than 1 over S naught, and delta L has to be 1 over less than 1 over T. If you have to plot delta L inverse and 1 over S, and also delta L and 1 over T, this is what you see. And you see a crossover region here. Okay? For this particular plot, you're asking for delta L inverse to be less than 1 over S. So in this, over at this side, it's perfectly fine. Yeah? Because at this side, the delta L inverse is less than 1 over S. Okay? And here it's not. For this plot, we're asking for delta L to be less than 1 over T. So on the right hand side, delta L is less than 1 over T. So this part is fine. Okay? This part is not. Alright, if you put them together, alright, you will notice that for low frequencies, yes, indeed, you have delta L inverse less than 1 over S. High frequencies, you have delta L less than 1 over T. But there's also a crossover region, whereby you are not sure. Okay, and we say that this crossover region is very critical. It's called critical frequency region. And in this crossover region, what we want to do is we want to avoid peaking of S and T. Okay, so that changes in the plant will not cause a serious loss of performance. Alright? Okay, so that in this crossover region, peaking of S and T needs to be avoided. ST is so that changes in plant will not cause serious loss of performance.